Back to our channel. We are in chapter 56 from Guyton, that is ventilation. We are in our respiratory physiology. So as usual, let us start with our glossary terms, important glossary terms. So the first one is alveolar ventilation. So in the name itself, understand ventilation means actually the breathing process which is going on in alveoli. Let us understand this definition. Alveolar ventilation per minute is defined as the total volume of new air entering the alveoli and the adjacent gas exchange areas each minute. It does not include dead space air. So alveolar ventilation means no dead space air. Means you know what is dead space air? The air which is not used in exchange of gases. But in alveoli, you know, the air is used for the exchange of gases. So here the dead space air is not included. But again, let us say alveolar ventilation per minute is defined as the total volume of new air entering the alveoli. So the amount of new air which is entering the alveoli is mainly called as alveolar ventilation, and the adjacent gas exchange areas for each minute, not only to the alveoli, even the new air which is entering to the adjacent gas exchange area. This is called as alveolar ventilation. Next, let us see the breathing reserve. The difference in maximum voluntary ventilation and maximum ventilation measured during exercise is the breathing reserve. There is a difference, means subtracting the difference in maximum voluntary ventilation and maximum ventilation measured during exercise. So normal, how much you can do ventilation, that minus the ventilation which is done in exercise. The difference between them gives the breathing reserve. And next coming the maximum voluntary ventilation. So the largest volume air that an individual can breathe into and out of the lungs in 1 minute with maximum voluntary effect. So the maximum voluntary ventilation means it is like in forced expiration and forced inspiration. It involves both sides force, that is forced inspiration and forced expiration. The maximum amount of air which you can take inside the lungs and maximum amount of air that you can bring out of the lungs, that is the maximum voluntary ventilation. Next coming to the minute respiratory volume. So the total amount of new air which is moved into the respiratory passage each minute. So for each minute how much amount of new air is entering, that is called as minute respiratory volume. In the name itself you can see for 1 minute. For 1 minute how much new air is entering, that is called as minute respiratory volume. It includes the dead space air also. So this is very important. In the case of alveolar ventilation, the dead space is not included because you know alveoli are the correct size of gas exchange, correct site, but you know dead space is the air which is not involved in gas exchange. So alveolar ventilation does not include dead space, but minute respiratory volume includes the dead space because it is not alveoli. So that is the main difference. So next coming to the partial pressure. So the total pressure which is exerted by a mixture of gases. Mixture of gases is giving a total pressure. Being the sum of all the individual pressures exerted by each gas in mixture, the individual pressures are referred to as partial pressure for each gas. So once again let us see the total pressure which is exerted by a mixture of gases being the sum of all the individual pressures exerted by each gas in mixture. So the individual pressures are referred to as partial pressure. So what is partial pressure is, you know, if we mix all gases together, they give one pressure, that is total pressure. But in that total pressure, each gas has its own pressure. That individual pressures of a gas is called as partial pressure. So now let us start our main discussion with the minute respiratory volume. As we discuss for 1 minute how much amount of new air can enter the respiratory passage. Even here the dead spaces are involved. So let us see about this. This is also called as minute ventilation. So the total amount of new air moved into the respiratory passage for each minute is called minute ventilation. So minute ventilation formula is tidal volume into respiratory rate. So we know what is tidal volume. It's 500 milliliters into respiratory rate. So actually what is respiratory rate? Respiratory rate is also equal to 12 minute inverse 1. So respiratory rate is 12 minutes and tidal volume is 500. So 500 milliliters into 12 minutes will give us a total minute ventilation of 6 liters or 600 milliliters per minute. So the minute ventilation formula is tidal volume into respiratory rate. Tidal volume is 500 milliliters, respiratory rate is 6. So 6 into 500 milliliters gives us 6000 milliliters per minute or 6 liter per minute. So 6 liter per minute, you know, it's already the total lung capacity, and even this 6 liter per minute is also the minute ventilation. So with this with this minute ventilation, a person can live for a short period with 1.5 liter per minute and 2 to 4 breaths per minute. So in this minute ventilation, you can expect the 5 liter per minute of air, new air entering into the respiratory passage, and also in this 5 liter per minute of new air entering, a person can have 2 to 4 breaths per minute. So respiratory rate rise to 40 to 50 minute, and tidal volume can be as great as vital capacity 406 4600 milliliters in young adult man. Then it can give the minute respiratory volume greater than 200 liter per minute or more than 30 times the normal. So sometimes as the values increase, as the tidal volume is increase, you know and the vital capacity is increased, then even the respiratory rates can be greater than 200 liter per minute. Normally it's 6 liter, but sometimes if we try to increase them, like we are talking about their maximum can also be like 200 liter per minute, that is more than 30 times the normal. So more people, the people of like one half of the people or two-third of the people, for them these values can't sustain, they can't sustain these values for longer than 1 minute, hence the name here the minute ventilation. So this volume, like the 6 liter per minute, is sufficient for 2 to 4 breaths in 1 minute. So in 1 minute we can have this volume, but greater than 1 minute, like more than half of the people or two-third of the people can't sustain it, we need other sources for ventilation. So this is only, hence the name minute ventilation, that is the ventilation which we can sustain only for the 1 minute. So next let us see what is alveolar ventilation. So already we discussed in alveolar ventilation the dead space is not involved. Let us see the new air reaching alveoli, alveolar sacs, alveolar duct, respiratory bronchioles together called the alveolar ventilation. So the importance of pulmonary ventilation to exchange the air in proximity to the pulmonary blood. Actually our air is, alveolar sacs are in very proximity to our pulmonary blood capillaries. So because of that only there is rapid exchange between the capillary and the sac, alveolar sac. That is, it takes carbon dioxide from the blood vessels and gives oxygen from the alveoli to the blood vessel. So alveolar ventilation per minute is the total volume of new air entering the alveoli and adjacent gas exchange areas for 1 minute. So it is equal to the respiratory times amount of new air that enters these areas with each breath. So for this we have a formula again. VA is the volume of alveolar ventilation per minute, that is equal to the frequency of respiration per minute into VT minus VP. Here VT is the tidal volume, VD is the physiological dead space volume. We always need to remove the dead space volume because here it is not included. So the tidal volume, already we know that tidal volume also have some, actually tidal volume is mixture of both normal air and a dead space air. So we need to even remove it. So from the tidal volume we need to remove the dead space air so that we can get the pure alveolar ventilation without any dead space air. So normally the tidal volume is 500 milliliters, right? And the normal dead space is 150 milliliter, and the respiratory rate is 12 beats per minute. So let us substitute all of them into this. So alveolar ventilation is equal to 12 into the frequency of respiration per minute is 12 beats per minute. As our heart, it has 74 beats per minute, like that the respiratory rate is 12 beats per minute. So 12 beats per minute into 500. Why 500? Tidal volume is 500 minus VD. VD is our dead space volume is 150 milliliter minus 150. So we get a 4200 milliliter per minute. So we need to remember all these values, these are very important. This 4200 uh, milliliter per minute is a value of alveolar ventilation, whereas for minute ventilation we have got a total of 6000 milliliter per minute, or also like 6 liter per minute. So this 6 liter per minute is a minute ventilation, and alveolar ventilation is 4200 milliliter per minute. So next, the alveolar ventilation, the major factors determining the concentration of oxygen and carbon dioxide in alveoli. So very important, the factors which mainly determine the oxygen and carbon dioxide concentration in alveoli are alveolar ventilation. So now let us see the maximum voluntary ventilation. So maximum voluntary ventilation, as before we have seen in the definition, the maximum amount of inspiration and the maximum amount of expiration which we can do during breathing is the maximum voluntary ventilation. So it is a shortcut as MVV. It is the largest volume of air that an individual can breathe into and out of the lungs just in 1 minute with a maximum voluntary effect. So it is usually measured for about 10 to 15 seconds and extrapolated for 1 minute. So actually it is only for 10 to 15 seconds, but we will try to exaggerate it. We try to drag it to 1 minute. So MVV is equal to the volume measured in 10 seconds into the 60 seconds by 10 seconds, that is equal to the volume measured in 10 seconds into 6. So this is the formula which we need to use here. So MVV is usually expressed in liters per minute. So now here we are going to check out the diagram of alveolar ventilation. So you can see this is the pre-inspiratory phase, the first one, second one is an inspiration phase, and the third one is an end inspiration phase. So in the pre-inspiration you can see that the gas in the alveoli, in that alveoli 150 milliliter may be dead space air, and the tidal volume is 350 milliliter plus 150, together it gives 500 milliliters. We know tidal volume is 500 milliliters. And in the inspiration you can see the dead space 150 milliliters is in the inspiration itself, and this 150 milliliter is conducting airways in the lung. So the dead space has now come out into the conducting airways at the time of inspiration, because in alveolar ventilation we will not accept the dead space, so we need to remove the dead space, that is 150 milliliter. So only this 350 along with 150 together form the 500. Only the tidal volume is accepted in the case of inspiration. So coming to the end of inspiration. So at the end of inspiration you can see the gas in the alveoli, again the dead space has come to normal, remaining in airways from preceding breath. So even from the preceding breath some of the dead space volume may be remain. So that one, and the tidal volume. So this is like a diagram which shows pre-inspiration phase, inspiration phase, and end inspiration. So here we can see one more diagram with a comparison of alveolar ventilation with minute ventilation and anatomical dead space ventilation. So let us see three of them. So here three subjects, means three persons are involved in this experiment. In the first one the tidal volume is 150, in the second one it's normal 500, whereas in the third one it's double, that is 1000. So the respiratory rate per minute in the 151 will be 40, in the normal one it is 12 minutes, and in the 1000 one it will be 6. So anatomical dead space ventilation we can calculate it as 150 into 40. So already we know the formula to find out this. To find the anatomical dead space ventilation, we need to do tidal volume into respiratory rate. So tidal volume into respiratory rate, 150 into 40 you get 6000, 500 into 12 we get 1800, 1000 into 6 we get 900. So these are the values in milliliters we have got. Those are the anatomical dead space ventilation. And next coming to the minute ventilation. So minute ventilation is nothing but these values directly. Minute ventilation is same for three of them, 6000, 6000, 6000. Whereas coming to the alveolar ventilation, actually we know the minute ventilation formula as we discussed in our theory part. So here you can see the minute ventilation formula we already know, that is tidal volume into respiratory rate. So what is the tidal volume here? Respiratory rate. So tidal volume into respiratory rate, actually here we use respiratory rate as 6. So here you can see, as we already did here calculations, respiratory rate we are using 12. So if you do this into 12 we'll get 6000. And next coming to alveolar ventilation. So you know already alveolar ventilation formula. So alveolar ventilation formula is frequency into VT minus VD. So by using this formula we get these values. For the first one it's 0, and the second subject it's 4200, and the third one it is 5100. So like this we need to find out the values according to the formula as we discussed before. So now let us move on to breathing reserve. So breathing reserve shortcut is BR. So BR is nothing but the difference in the maximum ventilation, uh, it's a difference in the maximum voluntary ventilation and the maximum ventilation measured during exercise. So now we are going to take the difference when the maximum voluntary, you know what is maximum voluntary ventilation, that is the maximum inspiration and the maximum expiration we do, minus the maximum ventilation which is measured during exercise. Because why they are actually comparing this both, you can understand now, because in exercise also we use forced expiration and forced inspiration. So that is the reason why we are going to take out the difference between those. So that is called as mainly breathing reserve. So breathing reserve for 1 minute is equal to maximum voluntary ventilation minus maximum ventilation during exercise. So that is equal to, and it is divided by MVV into 100. MVV is again the maximum voluntary ventilation into 100. So normal the BR is between 20 and 50% of the maximum voluntary ventilation. Individuals with low breathing reserve may be limited in either in their exercise capacity due to limited ventilatory. So actually the normal value of this calculated breathing reserve is between 20 and 50%. But sometimes the people may find in that some people it may be low. So in that people, when this breathing reserve is low, we can find out that these people have not much capacity to do heavy exercises, because in their exercises their breathing reserve may fall down. So they have limited exercise capacity and limited ventilatory capacity. So like this we can compare and understand the ventilation capacity during exercise. Now let us move on to the gas pressure in mixture of gases, that is partial pressure of individual gases. So pressure is the directly proportional to concentration of gas molecules. So the mixture of gases like for example oxygen, nitrogen, carbon dioxide, the rate of diffusion of each of these gases is directly proportional to the pressure caused by the gasoline. So which is called partial pressure of that gas. So partial pressure is nothing but about individual gas. The individual gas which can produce how much pressure, that is called as the partial pressure of the gas. So air, for example, in air we have 79% of nitrogen and 21% of oxygen. So the total pressure of this mixture at sea level averages about 760 millimeters of mercury. So in that 79% of this 760 is caused by the nitrogen, that is like about 600 millimeters of mercury, and the 20% 21% is caused by the oxygen, that is 160 milliliters of mercury. So together 600 plus 160 you get the 760 again. So in this total of 760 there is partial pressure of like 79% of nitrogen and 21% of oxygen. So if we try to find out that values, we get 79% of nitrogen gives us 600 milliliters of mercury, and 21% of oxygen tries us to give 160 milliliters of mercury. So the symbols which can use for the partial pressure of individual gases is partial pressure of oxygen PO2, PCO2, PN2, PH2. This is partial pressure of carbon dioxide, partial pressure of nitrogen, partial pressure of hydrogen. So now let us see the pressures of gases which are dissolved in water and tissues. So if the gases are dissolved in water and tissues, what happens? So the gases which are dissolved in water exert the pressure because of dissolved gas molecules are moving randomly and they have the kinetic energy. So because of the kinetic energy they try to give the pressures there. So the gas molecules which exert their partial pressure on surface of water. So mainly the gas molecules when they are put or when are dissolved in the water, they try to always show the partial pressure mainly on the surface of the water. So here also we call them same like partial pressure of oxygen, carbon dioxide, nitrogen, hydrogen or helium. So the partial pressure of gas in a solution is mainly determined not by the concentration but also by the solubility coefficient of gas, that is the carbon dioxide physically or chemically attracted to water, whereas other types of molecules are repelled. So not only here the solubility is dependent on like concentration, but how much it is like dissolved in the water, how much that is a solubility coefficient of gas. For example, if you take carbon dioxide, how much carbon dioxide is attracted to water, that we need to measure. But some particles are also repelled. So the molecules are attracted, far more of them are dissolved without building excess partial pressure within the solution. So always remember, if you are observing any in any solution the partial pressure is very high, means they are not perfectly dissolved. If they are perfectly dissolved in that specific solution, means they indicate that they are not having higher partial pressures. But in repelled molecules, increase in partial pressure will develop with fewer dissolved molecules. So now let us see what is Henry's law. Henry's law, partial pressure is equal to concentration of dissolved gas by solubility coefficient. So partial pressure is expressed in atmosphere is 760 millimeters of mercury, and the concentration is expressed in the volume of gas which is dissolved in each volume of water. So the solubility coefficient for important respiratory gases at body temperature are like for oxygen it's 0.024, for carbon dioxide is 0.57. So among this oxygen and carbon dioxide you can see that carbon dioxide is more than 20 times more soluble than oxygen. So you can see carbon dioxide is 20 times more soluble than oxygen, because you can see this value is 0.57. It is just 0.024, means it's very high, 20 times higher than the oxygen in the case of solubility. So now you can predict, is carbon dioxide is more soluble. If carbon dioxide is more soluble, means its partial pressure will be low. Just now we have discussed the gas which is not soluble only will have the higher partial pressure, as this carbon dioxide is more soluble, so it will have low partial pressure. But oxygen, you can see it is having low solubility, so it will have the higher partial pressure. So remember, partial pressure and solubility are inversely proportional. And next, therefore, partial pressure of carbon dioxide for given concentration is less than 1 by 12 of exerted by the oxygen. Oh, sorry, not inversely proportional, they are directly proportional. If higher solubility means higher partial pressure, so that's why Not they're inversely proportional only. Partial pressure is inversely proportional to solubility. This is fixed. Don't change it. Inversely proportional to solubility. So that's why you can see here carbon dioxide is more soluble. As carbon dioxide is more soluble, it is having less partial pressure. Partial pressure carbon dioxide is less than. That's why you can see carbon dioxide is more soluble. Highly soluble means low partial pressure. Hence, the partial pressure of carbon dioxide is low than oxygen. So, by this we can say that oxygen is having higher partial pressure when compared with carbon dioxide, because carbon dioxide is having more solubility. Then partial pressure will be low. So, here I'll write here carbon dioxide is more soluble means less partial pressure, whereas oxygen is less soluble means oxygen is having higher partial pressure. So here we can also check out the other gases values of partial pressure. So for oxygen 0.024, the solubility of course for important, this is the solubility not partial pressure. So this is 0.024, for carbon dioxide 0.57, carbon monoxide 0.018, nitrogen 0.012, helium 0.08. So by this we can predict among all this carbon dioxide is having highest solubility. Highest solubility means they are inversely proportional to partial pressure, so low partial pressure. So among this, which is having the lowest solubility, let us find out. 0.008. So helium is having low solubility, means helium is having higher partial pressure. So like this we need to we can easily find out the solubility. With the solubility values we can easily find out the partial pressure. Now let us see the relationship between alveolar ventilation and partial pressure of oxygen and carbon dioxide. So oxygen concentration and partial pressure in alveoli are mainly controlled by the rate of absorption of oxygen into the blood and the rate of entry of new oxygen into the lungs by ventilatory process. So let us see here this graph. So here you can see on x-axis we have alveolar ventilation and on y-axis we have alveolar partial pressure of oxygen. So you can see as the ventilation is keep on increasing on the x-axis, the partial pressure of oxygen is also keep on increasing. So you can see at the value of 4, that is you can say the point A, the partial pressure of oxygen has increased to 250 milliliter of oxygen per minute. It is upper limit of maximum ventilation in oxygen, partial pressure of oxygen. This is a normal alveolar oxygen at the level like between 100 and 125. And you can see this is a 1000 milliliters of oxygen per minute, which is starting at 0, and it is like between 15 and 20 when case of ventilation. So actually mainly what you need to observe here is as alveolar ventilation is keep on increasing like even like 30, 35, 40, but you can see here the partial pressure of oxygen is maintaining a plateau here. It is not further increasing. Only at the starting it has increased, but later it is forming a plateau. So by this you can understand that even though if you increase alveolar ventilation greater than, but the alveolar partial pressure may be in plateau, it is maintained in a normal value. So here we also have another graph which is showing on x-axis again alveolar ventilation, on y-axis partial pressure of carbon dioxide now. So because